Welcome to the fifth session of Finite Automata. In this current session, we are mainly discussing about regular expressions. What is meant by a regular expression? How a regular expression can be converted into finite automata. In this session, we discuss these two things. What is a regular expression and how it is related to regular language, and also how a regular expression can be converted to finite automata. The language accepted by finite automata, it is known as regular language. The language is described by simple expressions. Such expressions can be considered as regular expressions. The language accepted by finite automata can be easily described by the simple expressions called regular expressions. It is the most effective way to represent any language. The languages accepted by these regular expressions are known as regular languages. A regular expression can also be described as a sequence of patterns that defines a string. The sequence of alphabets, the sequence of symbols, the pattern of symbols that define a string. These expressions can be used to match character combinations. For string searching algorithms, we can use these regular expressions to check whether a particular string is present in another string or not, whether a set of characters is a part of string or not. For the various string operations, string concatenation, string copying, etc., we can use this regular expression. Regular expressions are used to match character combinations in strings. String searching algorithm use this pattern to find the string operations on a string. For instance, in a regular expression, x star means 0 or more occurrence of x. X plus means 1 or more occurrence of x. In the previous sessions, we already discussed about leen star and leen plus. Leen star is x star here and leen plus is x plus here. X star, the leen star of x means it can generate 0 or more occurrences of x. The 0 occurrence of x, that is the null string, is denoted as epsilon here. We can use either the symbol lambda or epsilon. Those things we discussed in the previous sessions. In a regular expression, x plus means 1 or more occurrence of x. It can generate 1 or more occurrences of x, that is x plus, the closure of x, leen plus. Then moving to the various operations on regular language. The various operations on regular language are mainly union and intersection. First, we are discussing about union operation. If L is a regular language and M is also a regular language, then L union M is also a regular language. If L and M are two regular languages, then their union L union M is also a regular language. L union M is equal to set S such that L is in S is in L or S is in M. S can be either in L or in M. The second operation is intersection operation. If L is a regular language and M is another regular language, then their intersection is also a regular language. L intersection M, set as such that S is in L and S is in M. It must be both in L and M. And third, lean star and lean closure is specified in a single area. If L is a regular language, then its lean star is L star. Lean closure is lean plus is L plus. It will also be a regular language. L star will be a regular language. L plus will be a regular language. You know what is L star. 0 or more occurrence of language L can be used as L star. 1 or more occurrence of language L can be denoted as L plus. Consider a set of examples. Here I am specifying a large set of examples. First one, regular expression R is equal to null set. Then the language over that regular expression R can be defined as a null set. The set without any element. It is corresponding to the regular language. Then second example, R is equal to epsilon. Epsilon you all know, a string with length 0, a null string, an empty string with length 0. Then the language over that regular expression is equal to set epsilon. And third example, R equal to A. R equal to A, regular expression R equal to A. Then the language over that regular expression is equal to set A. Then fourth example, the regular expression R equal to A plus B. Plus can be represented as a union operation. The product can be represented as an intersect operation. So for the language over that regular expression A plus B, we can represent as set A comma B, A comma B, either A or B, A comma B. The next example, R equal to A dot B. The language over that regular expression is equal to set AB. It's a single element, intersection of both A and B. A and B is a single element in that set. Then sixth example, regular expression R equal to A plus B plus C. The language over that regular expression R equal to set A, comma B, comma C, union of three elements A, B and C. Then consider next example, regular expression R equal to AB plus A dot B. Consider the expression is an arithmetic expression, A plus B into C. Then what we will do? AC plus BC. Here we can expand it as ABB plus AB. ABB plus AB. Then that elements can be represented in the language as set ABB comma AB. Consider the eighth example, R equal to A plus, the closure of A, lean star of A is represented as one or more occurrences of A. Then next one, R is equal to A plus. We already know the lean star of A, 0 or more occurrences of A. Then move to the 10th example, regular expression R is equal to A plus BA into B plus A. Expand the expression, AB plus AA plus BAB plus BAA. Then there are four elements AB, AA, BAB and BAA. And the language over that regular expression is equal to set AB, AA, BAB and BAA. Move to the next example, R equal to A plus epsilon into B plus null set. Similarly, expand it and reduce, we can get the elements at AB comma B. Then A plus B the whole square. Power 2. Power means concatenation. Concatenating A plus B with A plus B. A plus B into A plus B. then expanding AA, AB, BA and BB. This is the language. Then lean star of A plus B can be obtained as any occurrences including epsilon, epsilon A, B, AB, AA, etc. And in the last example, A plus B star dot A plus B. A plus B star we know the previous example set epsilon A, B, AB, etc. Dot A plus B. Dot A plus B. Solving we get the closure of A plus B. One or more occurrences of A and B. A plus B plus. That is the lean closure, lean plus of A plus B. Then moving to the second set of examples. Suppose you are provided with a statement. Write the regular expression for the language accepting all combinations of pairs over this set sigma is equal to set A. All combination of A means it may be zero occurrence of A, single occurrence of A, any occurrences of A. All combinations. All combination of A. If A is appearing 0 time, it means that it is a null string. That is, we expect the set of set epsilon comma, AA comma, etc. So it is clearly the lean star set of A. Lean star of A. So we give the regular expression for this statement as regular expression R is equal to A star. That is lean closure of A. Consider the second statement. Write the regular expression for the language accepting all combination of A except the null string. From the previous statement, null string is omitted. It is clearly the lean plus. Already we know it is clearly the lean plus. So no further explanation is needed for that. Then move to the third statement. Write the regular expression for the language accepting all the string containing any number of A's, any number of B. Any number of A and any number of B. For any number we know that it is lean star. 0 or more occurrence, it is lean star. But here we have two different alphabets or two symbols A and B. We have to perform union operation of A and B, A plus B, the lean star of A plus B. The regular expression will be A plus B star. It gives any combination of A and B. The lean star of A plus B shows any combination with A and B even a null string. So always keep in mind the lean star of A plus B shows any combination with A and B even a null string. Consider another statement. The alphabets here is 0 and 1. Instead of A and B, here I am using 0 and 1. In some applications, especially in theory of computation, we are mainly using the symbols, binary numbers. So write the regular expression for the language accepting all the strings which are starting with 1 and ending with 0. Over sigma is equal to set 0, 1. It is specific, it is defined two things. The start symbol must be 1 and the end symbol must be 0. So it can be 1 0, 1 1 0, 1 0 0, etc. Any combination. But the start symbol must be 1 and end must be 0. In between, 0 or more occurrences of zeros and ones can be obtained. In a regular expression, the first symbol should be 1 and the last symbol should be 0. Then the regular expression will be 1 0 plus 1 star 0. 1 the lean star of 0 plus 1 0. Then move to the next example. Next statement. Write the regular expression for the language starting and ending with A. and having any combinations of B in between. Similar to previous one, start with A, end with A. It is defined. In between we can have 0 or more occurrences of B. Clearly it is B star. Then the regular expression will be A B star A. Then to the next statement, write the regular expression for the language starting with A but not have consecutive B's. A can be repeated but not having consecutive B's. So it may be A, AB, AAB, ABA, AABA, like that. A can be repeated but B cannot be repeated. For that, the regular expression for the above language can be built as A plus AB. A can be repeated, A plus AB star, the lean star of set A plus AB. Then consider another statement. Write the regular expression for the language accepting all the string in which any number of A's is followed by any number of B and it is followed by any number of C. Three alphabets A, B and C of any number. Any number is lean star. Any number of A is A star. Any number of B is B star. Any number of C is C star. Then the regular expression will be A star, B star, C star. Then consider another statement. Write the regular expression for the language over alphabet sigma is equal to set 0 having even length of string. Here there is only one alphabet, one symbol 0, but the string must have even length 0, 2, 4, 6, etc. So the regular expression for the above language can be written as R is equal to lean star of 0, 0. Lean star of 0, 0. Then move to the last example or the last statement. Write the regular expression for the language having a string. It should have at least one 0 and at least one 1. The solution can be regular expression R is equal to 0 plus 1 star 0, 0 plus 1 star 1, 0 plus 1 star plus 0 plus 1 star 1, 0 plus 1 star 0 and 0 plus 1 star. Union of two terms 0 and 1s are interchangeable. That will be the regular expression. Then we shall move to the second part, how these regular expressions can be converted to finite automata. Conversion of this regular expression to finite automata. To perform this conversion, we are using a technique or an algorithm known as subset method. Subset method. This method is used to obtain finite automata from the given regular expression. The algorithm is given below. It consists of three steps. The first one is design a transition diagram. A transition diagram is a non-deterministic finite automata that having empty string. From that transition diagram, we have to eliminate the empty string and form a non-deterministic finite automata without an empty string. So first step, construct NFA with empty string, that is construct a transition diagram. Then second step, obtain the equivalent NFA. If we have a non-deterministic finite automata, we know how to convert it into deterministic finite automata. In the previous session, we already discussed about how to convert NFA to DFA, and after that, how DFA can be minimized. The last session we discussed already. So the third step is to convert the obtained NFA to equivalent DFA. This is the algorithm, simple algorithm. We shall explain with an example. Consider a regular expression. Design a finite automata from the given regular expression. 1 0 plus 0 plus 1 1 0 star 1. A regular expression is given. 1 0 plus 0 plus 1 1, 0 star 1. We know plus is the union, either or. Product is the intersection, and star, lean star, 0 or more occurrences means repeating multiple times, means that it is a loop. So first we construct a transition diagram. For the transition diagram, here I use Q0 to denote the initial state and QF to denote the final state. In between, a single arc is drawn and that expression is labeled in the arc. From Q0 to QF, QF is the final state. The expression is placed in the transition diagram. 1 0 plus 0 plus 1 1, 0 star 1. We have to expand the diagram. We have to construct the NFA. For that, we are continuing to step 2. In our previous diagram, analyze that regular expression provided. 1 0 plus, the first symbol obtained is plus. From that plus, we split the expression into two, the left hand side of plus and right hand side of plus. The left hand side of plus and right hand side of plus. This step 2, we can view the left hand side is a path from Q0 to QF. The plus form two parallel paths. The product forms a sequential path. From Q0 to QF, now we have two different paths. The first path is 1 0, the LHS of plus. The second path is the RHS of plus. The first path we have 1 and 0. 1 followed by 0 is the product. It means that there must be an intermediate node or intermediate state between Q0 and QF. I denote it as Q1 and represented in step 3. From Q0 to Q1, the label value is 1, and from Q1 to QF, the label value is 0. This completed that path is completed from Q0 to QF. In the second path, Q0 to QF, in the bottom part, the expression also divided into two. 0 plus 1 1 is the first expression. 0 star 1 is the second expression. So an intermediate state is provided there, a Q2 node, and left of Q2 0 plus 1 1 and right of Q2 0 star 1 is placed. Again we know that the left is an expression 0 plus 1 1. There is a symbol plus. So two different paths should be represented there. Right side 0 star 1. The star denotes a loop. So in the next diagram, from Q0 to Q2, 0 plus 1 1 is same as the previous one. But the right side of Q2, it is changed. The 0 star, the loop is represented in the Q2 itself. And the remaining of the expression 1 is from Q2 to QF. Now you know how Q0 to Q2 can be expanded. There must be an intermediate node, and to that left of that node is 0 and right of that node is 1 1. 1 1 is a product, so a sequence is needed there. One more node or one more state should be needed there. It is represented in the step 5 next diagram. So this is the NFA. Here we have Q0, Q1, Q2, Q3 and Qf. 5 various states are there. 5 various states. In each arc or in each state we can see a single input alphabet. Single symbol is represented there. We have got a non-deterministic finite automata without empty strings or without epsilon. Then we know how to convert it into the deterministic finite automata. For that we need a transition table of this NFA. Then the transition table for the DFA is formed, and from that DFA can be constructed. Here I just represented the transition table of both diagrams. The left is the transition table of NFA. From that, the transition table of DFA is constructed, and based on that table, the DFA can be developed. And consider one more example. Here the regular expression is 1 1 star 0 1 star 0 1 star the whole star. This step 1, the corresponding transition diagram is represented. The regular expression is splitted in step 2, and again it is splitted in step 3. We get the NFA. The step 3 is the NFA. QF is the final state. Q0, QF and Q2. Step 3 is the NFA. From that, transition table should be formed, and from the transition table of DFA, the DFA can be constructed. So in the current session, we mainly discussed about regular expressions. In the first part, we discussed what is meant by a regular expression, what is a regular language, what are the various operations that can be performed on a regular language and regular expression. In the second part, we mainly discussed what are the steps or what are the steps to be followed while converting a regular expression into a finite automata. Okay, thank you.